All right, excellent. So I guess Juan Carlos and I have the arguably envious position of holding everybody back from lunch, so we'll do our best to keep it on time. Welcome everyone. I really appreciate everyone being here. So Juan Carlos and I will be representing a quick update from the ACS Door Heat Exchanger sub-project. And specifically, we want to talk about updates in terms of what's been going on in our community, in terms of the contribution of a requirements document, some community studies, and then harmonization with the ACF group. Just some quick introductions. My name is John Fernandez. I am a thermal engineer at Meta, and I am the sub-project lead for the ACS Door Heat Exchanger workstream. And with me is...
I am Juan Carlos Cacho Alonso. I am working for Rital in Germany. I am working in research and develop for IT cooling solutions. Yeah,
excellent.
Mostly for direct chip cooling 2 phases.
Awesome. So just a quick overview. So similar to the immersion and the cold plate work streams, the door heat exchanger work stream is basically in place so that we can focus on efforts that enable potential adopters to look at door heat exchangers as a solution for the growing interest in liquid cooling and to lower that barrier or demystify it to a certain extent. Now, some of y'all might think door heat exchangers have been around for a very long time. But as I've said, with the reemergence of the importance of liquid cooling, we believe that certain applications of the door heat exchanger can help enable people deploy high power and high density solutions. And we'll be touching upon that briefly in upcoming slides. But just to outline the recent efforts, we had a door heat exchanger requirements document for OpenRack v2 and v3 contributed in July, which is available on the contribution portal. So I encourage everyone to, if you're interested, to go there and download a copy of the document. We have community studies ongoing, which Juan Carlos will go over, specifically in terms of, okay, so you are interested in a door heat exchanger solution, but what does that represent in terms of actual cooling capability? Are there crossover points between the different applications of a door heat exchanger? So we're hoping with this community study that we hope to contribute as a white paper sooner rather than later, will help end users sort of understand what are the ranges or the brackets within which you could potentially deploy a type of door heat exchanger solution. And then at the end, we'll quickly go over some of the harmonization we've been doing with the ACF group, specifically in terms of how do you, what are the specific FWS or facility water system definitions or interfaces, and is a door heat exchanger solution compliant with that? So in terms of requirements for OpenRack v2 and v3, as I said, this information has already been contributed and is available on the portal. But it basically defines technical requirements and potential applications for a rack mount door heat exchanger to be used with OpenRack. And the document is divided into, I guess, different sections, talking about dimensions, the type of data center environment from both an air-side and a liquid-side standpoint. How do you define performance and metrology? How do you basically determine what's the cooling capacity of a door heat exchanger? We have monitoring and control in terms of defining the required and the recommended sensors, controls, and alarms. We have serviceability is very important. Obviously, a door heat exchanger is a massive assembly. And then talking about reliability and quality is you only want to deploy a solution if you know it's reliable. And most importantly is leak proof when you talk about liquid cooling. And then we have general environmental and regulations considerations when you adopt the door heat exchanger solution with an OpenRack v2 and v3. Oops. Since we've been talking about requirements, this requirements document in previous Open Compute meetings, just wanted to focus on a very quick update that you'll find in Appendix A of the document that's been contributed, which is because OpenRack v3 is still being developed as we are talking, we wanted to make sure that you could implement a door heat exchanger with OpenRack v3 that already has liquid cooling infrastructure in it. So specifically in terms of the blind mate interfaces that a bunch of people in this room have talked about in the rack and power workstream, specifically in terms of what are the general keep-outs, are there specific host lengths that you'd want to consider depending on how you mount your door heat exchanger solution and interface that with blind mate manifolds within the rack as well as either a CDU or a reservoir and pumping unit. And basically all these details can be found in the document under Appendix A. But with the information we know right now with the blind mate interfaces being developed with OpenRack v3, we have some high-level considerations that have been outlined in the document that we believe will be useful to a potential end user. So to my original point about a door heat exchanger being a legacy product, we also believe that there are different applications of a door heat exchanger. And they can be broadly classified depending on whether your facility has access to an FWS loop or not. So we basically classify them under air-assisted, traditional, and hybrid. And then over here, we just have a cartoon representation with the parametric baseline that your facility is only capable of providing 20 kilowatts of air cooling per rack. These are obviously just reference numbers. They don't represent the end user's data center. Obviously, those details change. So with the air-assisted liquid cooling solution, you are effectively bound by how much airflow your facility can provide at what temperature. But we do believe that the implementation, by reversing the traditional use of a door heat exchanger and doing liquid to air as opposed to air to liquid, and combining that with cold plates that are mounted to the really critical or hot components, it'll enable you to enable higher power components in an air-cooled facility where the cooling capability of a traditional heat sink may be somewhat limited. We then move on to what everyone knows as the traditional use case of a door heat exchanger, which involves either minimizing the amount of load that goes back to the room or making the rack itself room neutral. Obviously, over here, we claim 60 kilowatts, but that would have to be 60 kilowatts of a pretty dense rack that is 100% air-cooled. So the IT gear would have to be 100% air-cooled over here. And then we believe one really good implementation of a door heat exchanger is the hybrid solution, where you take the cold plate technology that's being developed across the industry and combine it with a door heat exchanger so that the amount of air cooling requirement from the facility is minimized, and you can put most of the load into the liquid. As well as, similar to the air-assisted solution, you have the advantage of the cold plates on the components that allow high power, high density components within the IT gear itself. And I'll hand it to Juan Carlos, who will talk about some of the community studies related to that.
So thank you very much, John. So what about if the density of the racks are improved and increase the power density of the racks? What are the limits of each solution, the traditional air-assisted and hybrid? Well, if the power density increase in the traditional rear door, you are increasing the power into the air. Also, therefore, this is the density, the maximal density of the racks could increase, but not too much, because there are some limits because of performance of the heat sinks. Also, if you want to increase the performance of the servers with this traditional rear door, we have to be able to reduce the temperature or the air temperature in order to be able to cool down the servers. And for sure, this is possible, but increase the energy consumption. In the air-assisted system, the power density could be increased a lot because you are able to use cold plates. So the power density of the rack increased a lot compared with the traditional system. The limitation of this technology is the very high flow rate, airflow rate, you have to use. And this is a problem because the space in the hot isole is limited. And yeah, if you want to increase the power too much, you have to increase also the capability of the data center if this data center is air-cooled. But depending on the temperature of the ambient, the efficiency could be really high because you have to move only the air through the servers. And we could use free cooling around the year. For sure, it is important to use only air. For the hybrid solution, you can increase even more the power density of the rack because most of the energy will come from the cool plates, and you can put out the data center with the water. So at least there are not too much limitation, only perhaps the airflow rate for secondary components, and yeah, the connections to the door could be difficult if the amount of water is very high. The efficiency is lower than the air-assisted solution because you have to cool down the secondary components with air. This air, you have to put the energy into the water, and after the water, you have to cool down with air again. And you lose a lot of efficiency in that way. But compared the using free cooling to cool down the cool plates, the efficiency could be high. Another community study was to what about the boundary conditions of the systems, all systems? For sure, the maximal and minimal temperature of the air input into the server is given by the servers. But after this temperature, all solutions have different boundary conditions, because if you are using cool plates or not, that changes everything. Therefore, we define the temperature after the racks is different if you are using one or the other technology. And for sure, the overall temperature difference is also different. If you are also, using, for example, the traditional solution, the overall delta temperature into the system is 0. Therefore, you have to put water with a temperature to keep the temperature into the data center so below your needs. These are interesting charts. If you see the build, the power of the system, the performance of the system is obviously proportional to the flow rate of the air and flow rate of the water. But if you want to increase the performance, you have to take care how much increase you the flow rate of the air or the flow rate of the water. For example, if you increase the flow rate of the air a lot, but not the flow rate of the water, you are not able to increase the performance of the system, and you increase the power consumption of the fan, but you don't reach too much performance. Therefore, there are optimized point in which you have to work. If you are using water and air, there is a combination to increase the efficiency of the system. This is the same, but fixing the temperature and the flow rate of the water. There is the approach temperature between the hot and cold temperature and by different temperature of the water. If you increase for sure the heat of the system, you can choose which temperature for water or air you want. but you have to take care about the system in order to increase the efficiency. There are many harmonization efforts. One of them was the connections and the delta T of the water temperature. We define the delta T of water between 7 and 13 Kelvin. So it means if the water is coming with 30 degrees, coming out with 7 Kelvin or 13 Kelvin more. This is something to fix a point in which the system are working. This is very important because if I'm not able to write something here, the possibilities are very large. And this is difficult to imagine in which point should be work the reactor, heat exchanger. Other important point is the thread type of the connections. We thought about different solutions, but the best idea was to use BSP parallel systems in order to avoid leakage into the system and lose water. And this is because also these connections are very common around the world. And we don't want to use connections that are specifically only for Europe, for US, or Asia. So the compatibility, also the compatibility with the system is very important also because the reactor have to work into a system, a bigger system like the data center. And the minimal pressure should be vacuum by 50 kilopascal, and the maximal breast pressure should be around 1,000 kilopascal. This is given by UL 6335, and therefore it's important to keep in mind. The specification about the water quality and the water content is also given. And you can find something more information in the S-Ray TC 9.9. So all important point is to be able to deliver 3D models. This is an important point, and these 3D models should be with a Revit format, and also the target site should be less than 700 kilowatts. This is really difficult. But this is very important because the data centers are very big. And if all suppliers are putting the 3D models with more than 700 kilobytes, will be impossible to put everything together. This is very important to keep in mind. To the 3D models, it's important to add information like the voltage, connections, electricity connections, water, and everything. Because this gives a lot of information for the customers who are want to put everything into a 3D model. So.
And just to round things off, just a call to action. We are always open to input. If you have certain questions regarding, okay, how do I, is there any guidance with regards to enabling door heat exchangers or any of the other solutions that we've just highlighted, please check out the links for the general ACS work stream, but also the door heat exchanger stream. And please get involved. We're always looking for input. We always want to know information on the facility side. We have a really good group of vendors who are already involved. Is there a specific problem that you'd like us to solve that could become a separate community study or community topic? So we are open to that as well. We have bi-weekly calls on Thursdays at 9 a.m. PST. We actually are meant to have one this week, but because of OCP, it's canceled. And then in 2 weeks' time, we have Thanksgiving, so we're going to be meeting next in December. But yeah, please check out the links and please get involved. One very quick thing, talking about air-assisted liquid cooling solutions, Yuming and Dennis are going to be talking about that at the end of the cooling environments track. It'll specifically talk about two different applications of AALC. One of them is a door heat exchanger, the other one's a sidecar. So if you're interested in learning more about that concept, please stick around and check out the last session in this track today. So thank you. Do we have any? Oh.
Any questions? We do have a few minutes.
Hi. So thank you for the presentation. I have one specific question to the slides where you show the three different types of the door heat exchangers. I personally don't understand the difference between the traditional and the air assistant version. Could you explain that a little deeper, please?
Sure, yeah. So the primary difference is the way the heat exchanger is designed, but also the heat transfer. So in the traditional solution, obviously, you're taking heat out of the air and putting it into facility water. Mm-hmm. With the air-assisted solution, the assumption is that your facility does not have any plumbing or liquid available. So the point over there is to, instead of doing air to liquid, as you would in a traditional solution, you're doing liquid to air. So basically, you deploy cold plates on the critical components in your IT gear, and then you use the door heat exchanger to exhaust that heat to air. So that's the main difference between air-assisted and traditional. Yes.
Okay, thank you very much.
Mostly it's also for air-cooled data centers, this solution.
Okay.
Good question. Anyone else?
With that said, I guess it's lunch.
Yeah, lunchtime, everyone. Thank you.
Thank you, everybody.
Thank you very much.